And the history of human spaceflight has, until very recently, been defined by a philosophy of spectacular waste. To appreciate the magnitude of the shift SpaceX is attempting with the Raptor 3, one must first confront the sheer absurdity of the traditional aerospace business model. Imagine a commercial flight from New York to London. A Boeing 747, a marvel of modern engineering worth nearly $400 million, carries 400 passengers across the Atlantic. Upon arrival at Heathrow, instead of taxiing to a gate to be cleaned and refueled, the pilots bail out over the English Channel, and the aircraft is allowed to nosedive into the sea, shattering into 1,000,000 pieces of aluminum and titanium. To get those passengers back to New York, the airline must build an entirely new 747 from scratch. And under such a regime, a single plane ticket would cost upwards of $1.5 million. International travel would be the exclusive province of billionaires and government-funded researchers. The disposable economy of 20th-century rocketry, from the Saturn V to the Space Shuttle's massive external tank, operated exactly like this. Every mission was a bespoke, artisanal event where the hardware was treated as a consumable. The Raptor 3 is designed to finally kill this paradigm. The goal is not just reusability in the sense of salvaging parts. The goal is the airline model, a reality where the vehicle lands, undergoes a cursory visual inspection, takes on a fresh load of propellant, and returns to the sky within a few hours. And from ephemeral functions to persistent systems, for those steeped in the world of software architecture, the transition from expendable rockets to the Raptor-powered Starship can be viewed as a shift from stateless to stateful infrastructure. In the legacy era, a rocket was essentially a lambda function, or a serverless execution. It was spun up for a single, ephemeral task, delivering a payload to a specific coordinate. Once the task was executed, the environment was destroyed. There was no need to worry about long-term system health, wear and tear, or bit rot in the hardware, because the hardware would be at the bottom of the Atlantic before any of those issues could manifest. And the Raptor 3, conversely, is a persistent server. It is high-availability infrastructure that must maintain its uptime across hundreds of duty cycles. In the old model, the primary engineering constraint was performance at all costs. The engine only had to survive for approximately 6 to 8 minutes of flight time. In the airline model, the constraint shifts to mean time between failures, or MTBF, and ease of maintenance. And when we look back at the rocket engine blueprint discussed in Chapter 1.2, the fundamental anatomy of the engine, the turbopumps, the combustion chamber, the nozzle remains recognizable. However, the operational philosophy has undergone a radical inversion. We are no longer designing a sprint runner who can finish one race before their heart gives out. We are designing a marathon runner who can wake up the next day and do it again. The Raptor 3 is the first engine in history where the design priority for turnaround time sits on equal footing with specific impulse. In the refurbishment trap, lessons from the shuttle. To understand why the Raptor 3 is a breakthrough, we must examine the refurbishment trap that plagued the Space Shuttle's main engines, known as the RS-25. On paper, the RS-25 was reusable. In practice, it was refurbishable, which is a vastly different and more expensive concept. After every flight, the RS-25s had to be removed from the orbiter, disassembled, inspected with ultrasound and X-rays, and often had their high-pressure turbopumps replaced or rebuilt. It was less like an airline operation, and more like a Formula One team rebuilding an engine between every Grand Prix. And the cost of this labor-intensive state reset meant that the shuttle never achieved the economic promise of reusability. The state of the engine, the microscopic cracks in the blades, the soot in the lines, and the degradation of the seals was too difficult to manage. And the Raptor 3 avoids this trap through the hardened kernel approach, by eliminating the vast majority of external plumbing, sensors, and soft tissue. As seen in the transition from Raptor 1 to Raptor 3, SpaceX has removed the components that typically require manual inspection. In an airline model, you do not pull the engine apart to see if it is okay. You rely on onboard diagnostics and the inherent robustness of the design. The Raptor 3 is intended to be a black box that maintains its integrity through hundreds of starts without human intervention. And reliability as a function of cycle count. In the traditional model, every engine was a special snowflake. Because so few were built, each one had its own quirks and idiosyncrasies. If an Atlas V or a Delta Roman 4 failed, it was often due to a one-off manufacturing defect that was never caught because the sample size was too small. In the airline model relies on the law of large numbers. By building a rocket every day and flying the same engines repeatedly, SpaceX is moving toward a deterministic safety model. When an engine has successfully fired 20 times, the probability of it failing on the 21st time is, paradoxically, lower than a brand new engine failing on its first flight. This is known in reliability engineering as the bathtub curve. Most failures happen either very early in a component's life, known as infant mortality, or very late, known as wear out. and by reaching a state where Raptor engines are broken in and then flown repeatedly. SpaceX is operating in the flat bottom of that bathtub curve, the zone of maximum stability. The Raptor 3 is designed to extend that flat zone for as long as possible. The move to a monolithic 3D printed structure for the major manifolds reduces the number of joints of failure. In the Airline model, every bolt is a potential leak path and every weld is a potential crack. By printing the engine as a single, continuous piece of metallurgy, SpaceX has compiled the hardware into a state that is far more resistant to the thermal cycling inherent in rapid reuse. And the gas station in the sky, refueling and state persistence, a critical component of the Airline model, is the ability to refuel. No airline could survive if planes had to return to the factory to get gas. For Starship, this means orbital refilling, the process of docking a tanker Starship with a mission Starship and transferring cryogenic methane and oxygen. And this is where the stateful nature of the Raptor 3 becomes a mission-critical requirement. In a typical lunar or Martian mission, the engines must perform a launch, shut down for days or weeks in the vacuum of space, maintaining their state in extreme cold, and then cold boot perfectly for a landing burn or a transplanetary injection. And legacy engines were never designed for this kind of sleep mode. They were designed to be pampered by ground crews, kept at precise temperatures by purge carts, and ignited under highly controlled conditions. The Raptor 3, however, is built to be environmentally agnostic. Its integrated cooling channels and internal heaters allow it to manage its own thermal state, much like a modern car's ECU manages the engine block temperature. This allows the airline to operate not just from a high-tech hangar in South Texas, but from a dusty pad on Mars or a floating platform in the Pacific, and eliminating the ground stack, the zero-touch interface. If you look at a photograph of a Raptor number 1, it is a forest of wires, tubes, and insulation blankets. To fly that engine again, a technician would have to check every single one of those connections. It is high-maintenance code, and the Raptor 3 looks like a smooth, metallic sculpture. This is not for aesthetics, it is for zero-touch operations. By moving the sensors and controllers inside the protective shell of the engine's primary structure, SpaceX has eliminated the ground, stacked the army of technicians required to prep a rocket for flight. And in the Airline model, the ground turnaround is the ultimate bottleneck. If it takes 48 hours to inspect the engines, you can only fly once every few days. If the engines are self-diagnostic, you can fly again as soon as the propellant tanks are full. The Raptor 3 internal system health monitor acts as an automated pre-flight checklist. It runs a high-speed self-test of all valves and ignitors. If the checksum matches, the engine is cleared for ignition. This is the difference between a manual deployment and a continuous deployment pipeline, and the economic threshold of good enough. To achieve the Airline model, SpaceX had to overcome the 99% perfection problem. In traditional aerospace, engineers strive for 99.999% reliability on the first try, which leads to astronomical costs. SpaceX realized that in a reusable system, you can afford a slightly higher failure rate during the development phase if it leads to a much lower marginal cost in the operational phase. And the Raptor 3 is the result of this optimization loop. It is not designed to be the most efficient engine possible in a vacuum. It is designed to be the most economically sustainable engine. If a 1% decrease in fuel efficiency allows for a 50% increase in engine lifespan, the Airline model dictates that you take that trade every time. This is a systems engineering approach that looks at the total life cycle of the hardware rather than a single mission's telemetry. And we are moving toward a world where the launch is the least interesting part of the mission. In the same way that you do not marvel at the physics of internal combustion when you board a flight to London, the goal of the Raptor 3 is to make the act of leaving the Earth boring. When the engines become a reliable, background utility, a hardened service that just works, the true exploration of the solar system can begin. And however, moving to a rapid reuse, airline-style cadence introduces a new set of bugs that legacy rocketry never had to solve. When you use a rocket once, you do not care about the residue left behind in the combustion chamber. But when you want to fly that same engine 10 times in a single week, the chemistry of the fuel itself becomes the primary antagonist. This brings us to the fundamental reason why SpaceX chose liquid methane over the kerosene used by the Saturn V and the Falcon 9. To keep the servers running without a reboot, you have to keep the system clean. And this requirement for pristine internal conditions leads us directly to the next major hurdle in the quest for the Airline model, addressed in section number 9.2, coking and soot, why methane wins for reusability.